Today we're going to get an introduction to series, and we're going to look at how we can determine if a series diverges and a couple ways that we can determine if a series converges. Okay, so first a little review of a sequence. A sequence is a list of numbers written in an explicit order. So we have the first term, second term, third term, on and on. And the series is the sum of all the terms in the sequence. So if we're looking to add up n terms, so the terms a sub 1 through a sub n, we would start with a sub 1 and we'd go all the way up through a sub n, add them all up together. We use the sigma notation here to denote that we're adding up all of these terms. What we're going to deal with most of the time is an infinite series, where rather than stopping at n, we just keep going and going and going. And it turns out, depending on the particular series, sometimes when we add up all of these terms out to infinity, the sum approaches some number, in which case we say it converges. If the sum does not approach some number, we say it diverges. Okay, so if we start with a square that's 1 by 1 and we cut it in half, the area of the left half is 1/2. Cut the remaining portion in half, that area is 1/4. And then we get 1/8, 1/16, 1/32, and so on. And you can see as we continue this pattern going all the way up into the corner of this rectangle here, the sum of all of these areas would be 1, although there would be infinitely many terms that we were adding together. So this is an example of an infinite series, and this is a series that converges because the sum of these numbers approaches some limiting value. And there are some series that do not converge. This series right here, 1/1 plus 1/2 plus 1/3, it turns out that actually approaches infinity, and we'll see here in a couple lessons how to prove that that series diverges to infinity. Okay, if we take a look at an infinite series, these values a sub 1, a sub 2, we call those the terms of the series. A sub n is referred to as the nth term, so we use n to denote some arbitrary term somewhere out there along the way. We can look at partial sums, which is just when you add up the first n number of terms. So if we take s sub 1, that's the sum of the first term. S sub 2 is the sum of the first 2. S sub 3 is the sum of the first 3. We could look at s sub n, and that's the sum of the first n terms. So we call that the nth partial sum. And as n gets really big, as n approaches infinity, if s sub n has a limit, so if s sub n approaches some number, we say that the series converges. Otherwise, we say that it diverges. All right, now we're going to look at a specific type of series, a geometric series. We've already looked at a geometric sequence. A geometric series is just when we add up the terms of a geometric sequence. So we have our first term, we'll call that a, and we multiply that by the common ratio r. So the next term is a times r, then a times r squared, and so on. And we can write this in sigma notation as the sum from n equals 1 to infinity of a times r to the n minus 1. And it turns out a geometric series always converges to a over 1 minus r if the absolute value of r is strictly less than 1. And a geometric series diverges if the absolute value of r is greater than or equal to 1. We call this inequality -1 to 1 the interval of convergence. So a geometric series converges for all values of r between -1 and +1. All right, let's take a look at this. This is a geometric series because we're multiplying each term by 1/10. We could write this in decimal form as 0.3 plus 0.03 plus 0.003. And you could maybe see from this form that if you add this together, this is just going to give you 0.3 repeating. So we can tell from this form that this series converges to 1/3. We could also use the formula that we just learned, a over 1 minus r. So a is the initial term, that's 3/10, over 1 minus the common ratio, which is 1/10. Simplify that down, and we end up with 1/3. So we're just showing here that we examined this in two different ways. In both ways, we came up with the same value for the convergence. All right, this is a geometric series. We're multiplying each term by -1/2. So a is the initial term, that's 1, over 1 minus r, so that's 1 minus -1/2. If we simplify this down, we end up with 2/3. So this series converges to 2/3. Okay, now if we look at any series in general, the requirement for a series to be able to converge is that the terms must approach zero. So we have the nth term test for divergence, which says that a series diverges if that limit as n approaches infinity either doesn't exist or is not zero. If that limit doesn't exist, if that limit doesn't go to zero, the series diverges no matter what. And what we really need to make sure we take from this is the nth term test can only show divergence. The nth term test does not show that something converges. If that limit as n goes to infinity of a sub n were zero, then that series still might converge, might diverge, and we'd have to find some other method to determine that. And that's what we'll be looking at for the remainder of this chapter. Okay, so we want to know if this series diverges. Well, we can take the limit as n goes to infinity. Using L'Hopital's rule, we end up with 1/3. So the limit of the terms of the sequence approach 1/3, which is not zero. So this series diverges by the nth term test. If we take a look at this one, take the limit as n goes to infinity. Applying L'Hopital's rule, we get 0, which means the nth term test is inconclusive. So we do not know if this thing converges or diverges. We'd have to figure out some other way to investigate further. And that's something that we will be able to figure out here in the next couple chapters, or in the next couple sections. Okay, just a reminder here of our geometric series. This is one of our methods for determining if a series converges or diverges, and it's all based on that common ratio R. And now we'll take a look at how we can determine if other series converge or diverge. One of the special types of series we can look at is a telescoping series. And a telescoping series is one where the middle terms all cancel out. So if we looked at this, we have the sum of 1 over n minus 1 over n plus 1. And it's going to be useful here to write out the first few terms. So if I start with n equals 1, I get 1 over 1 minus 1 over 2. And then I go to n equals 2, so I have plus 1 over 2 minus 1 over 3, and then plus 1 over 3 minus 1 over 4. And you can see that all of these middle terms end up canceling each other out. So our nth term would be the first term, 1, because that never cancels out, minus 1 over n plus 1. And if we take the limit as n goes to infinity, we end up with 1. So a telescoping series always converges to the first term minus the limit of that last term as n goes to infinity. So a telescoping series, just like the geometric series, not only tells us if the series converges or diverges, but what it converges to. And you'll see as we get further along here, not all tests are that powerful. Not all tests can necessarily tell us what something converges to. They can often just tell us if it converges or not. Okay, now this series is also a telescoping series, even though it might not look like it at first glance. But if we use partial fractions to split this up into two fractions, we can solve for a and b. So we've got a, we've got b. Turns out this series is the same as the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1, and that's the series that we just looked at. So again, we can write out the first few terms, see that these all cancel out. So the sum from n equals 1 to infinity of 1 over n times n minus 1 is equal to that first term that never cancels, 1, minus the limit as n goes to infinity of 1 over n plus 1, which turns out to be 0. So this thing converges again to 1. Okay, let's take a look at a couple properties of infinite series. So if we have two series here, one is the sum of a sub n, that converges to a, and the sum of b sub n converges to b, and let's say that c is some real number, then the following properties hold. If we have the sum of c times a sub n, that's the same as c times the sum of a sub n, which is equal to c times a. So that constant multiple can be moved inside and outside the summation. If we have the sum of a sub n plus b sub n, we can separate that and deal with each one independently. And same thing with subtraction.